infinity to 0. What does that look like? It's like kind of one of those, right? Decreasing concave down. Now you're increasing concave down, and now you're decreasing concave down again. Okay, so if you do all the calculus right, you do all the factoring right, you make the sign charts right, then you have everything you need to do the problem. So what's going on at 0? I have a relative minimum because my derivative changed sign from negative to positive. And also you can see that this function's not differentiable at 0, right? Because if you try to plug at 0, you get undefined. Not only is it not differentiable, but you can see why it's not differentiable, because it's blowing up to like infinity, right? So we should expect a sharp point here on my function, because it's not differentiable, and also we know the kind of sharp point. It's going to be like a vertical tangent line type situation. Yet it's concave down always, so it's maybe a little tricky to make this graph. So what's happening? Well, I know, and also I know that, let's see, well, whatever, let's do it. So if I have a relative min at, I guess I should plug in 0. So if I plug in 0, I get 0. And if I plug in 1, I get 3 minus 2 is 1. And what's happening at 1? At 1, there is a relative max, because my function, my derivative was positive and then negative. All right, so I have a relative min at 0, relative max at 1. What's the only way this function can look like, therefore, based on my number line concavity chart? It must go like this, and then like this, and then decreasing ever after, and I'll get a root somewhere. I couldn't even figure out where that root was if I factor this. So this original function was 3x to the 2/3 minus 2x. So I guess if I factor out the lower one, which is x to the 2/3, then I'm left with 3 minus 2 to x to the 1/3. If I did that correctly, just double checking. Yeah. Minus 2. So this is actually x to the 2/3. This is the original function now. And then there's I'll pull out a negative. And so it's like 2 cube root x minus 3. So actually, if I was kind of smart and didn't even know any calculus, I bet I could still sort of guess what this function was like. Because it's going to be locally bird at 0. And it's going to have a root at... Hello? It's going to have a root whenever this is 0. When is this 0? 27. Whenever 2 cube root x minus 3 is 0, which happens when cube root x is 3/2. So it's happening at 27/8. So over here at 27/8, that's when this is going to cross. Cool. So this is the whole function. Relative max at 1, 1, kind of a traditional relative max, and a relative min at 0, 0, which is like a sharp point. And in fact, what's happening to these tangent lines as they get really close to 0, they're like infinitely, right? Here the slope is like negative infinity, and here the slope is positive infinity. And then we go down. All right, how are we feeling about this? That took way too long, by like a factor of double. So hopefully you learned off of that.
Yes.
How are we doing? Good.
Better than normal.
Good. Better than normal. Whoa. Okay. All right. We have time, therefore, for like maybe to go over like one optimization problem. Which one should we do? 35. 35. Is that cone in a sphere?
Yes.
Yes. All right. Good. Classic calculus problem.
Although if we had time, 26 would also be nice.
26 would have been nice, but due to the poor handwriting of the people in period 3, I had to do all those problems all over again. Did you figure that out eventually? Where is it, Caroline? Small arithmetic mistake, it got fixed. It turns out 16/3 is bigger than 4, so therefore the second derivative is always negative, and therefore it's concave down. Good. All right. So the optimization was like a whole nother world, and these problems are kind of hard. I think one of the harder problems was number 35. Cameron, stop talking. find the volume of the largest right circular cone that can be inscribed in a sphere of radius r. Whoa. And they make a picture, and the picture is very helpful, I think. But had they not made the picture, then you should have made a picture. All right, so we have a sphere, and here's our sphere. And I want to put a cone inside this sphere, and I want the largest possible cone. All right, so first of all, you gotta kind of like feel these problems. Like, so here, let's do it like this-ish, and like this-ish, and we get a little bit like this. All right, and this is the face of the cone. Okay, so good. And I want to, and the radius of the cone is just r. All right, so let's go.
Wait, isn't that the radius of the sphere? Yeah,
Sphere. Radius of the sphere is r. Okay, how should we do this? We have only what? So we know the radius of the sphere is r. So a good hint whenever doing problems with circles or spheres is you have to somehow use the definition of a sphere. And the definition of a sphere is that like all the points are equidistant. So we should draw some radii in. And they even did this for you in the picture, which was extremely helpful. And this sort of starts to suggest how to do this problem. That this is r, and this is also r. And keep in mind that little r is a constant, so that's like important. All right, what I want to do is to find the volume of to find an expression for the volume of the cone, because if I can figure out the volume of the cone, then I can try to maximize it. Well, I need to like pick a variable somehow, and it's not obvious how to do it, and anything you do would work out, but it turns out that the smoothest thing to do is to let your variable be this number x. If I had also gone over number 26, in number 26 they tell you to do this. So number 26 was kind of a warm-up for the sphere problem, so I was hoping that like more than half of you thought to do this. If you didn't call this x, you could also have picked a variable for this one or whatever, but I think if you do it this way, it's smoothest. So what I'm going to do is I'm going to write an expression for the volume of this cone. That damn thing was a rumor that someone started. Totally false. All right. We should come up with an expression for the volume in terms of some variable. And I'm picking this variable. Is this what you guys did? Raise your hand if you did this. You called this x. Oh, like almost no one.
If you could get 26.
You could also do a variable for the whole thing. That works too. But I think this is smoother because then I get a very nice expression for the radius of the cone. What is the radius of the cone? Root r squared minus x squared. Alright, so now I'm just like ready to write the formula for the volume of a cone. And what is the formula for the volume of any cone? It's always just 1/3 of the volume of the corresponding cylinder. So it's 1/3 pi, and I'm going to use a different r just to make sure I don't confuse myself. I'll let big R be the radius of the cone, which is of course different from the radius of the sphere. Alright, so this is just pi over 3, and what's really nice about doing it this way is that as I'm squaring the radius of the cone, immediately like the radical disappears, and I'm back to, this is just a polynomial now, r squared minus x squared. And what is the height of the, it's just x plus r. Alright, so here I am, like one step into the problem, and it's like already kind of easy. Like I've done all the hard work already. All the hard work is in drawing a picture, labeling the picture, figuring out the relationships between the height and the radius of the cone versus the height and radius of the sphere, picking a variable to represent what's unknown, and also maybe it's worth like sort of thinking about the problem in advance, right? Like, why is this such a hard problem, finding the largest cone that fits? Because like, does everyone sort of let themselves think this through, right? Like if you try to make the cone taller, right? then as you pull these 2 points like down, yes, the cone gets taller, but now the radius of the cone gets smaller, right? Okay? And so that's like bad. If you try to make the radius of the cone as big as possible, that would be if the base of the cone were at the base of the, at the like sort of, yeah, like the equator of the sphere. But then my height wouldn't be so big. So somewhere there's like a happy medium in between, and that's like the whole goal of the problem. Okay, good. So now that I've expressed the volume of the cone as a function of x, I will just find the x which makes the volume as large as possible. Yes?
Quick question.
Yes.
Possibly, it looks like we could factor out the r squared minus x squared into x plus r, x minus r. Would
Yeah.
that be detrimental to our...
Yeah, so I think there are two ways to proceed from here, and both will work just fine. I could use the product rule, or I could just multiply this out and get a cubic and then differentiate like normal.
Okay.
I'm going to just use the product rule,
Okay.
just because I feel like it. You're proposing a different thing, which is factoring first, but I don't think that helps.
Yeah, I
out.
think
But
that just gets messy.
But you could do it. I think it would all be fine. But it's still just a polynomial, which is nice. All right, so leaving the pi over 3 on the outside and applying the product rule, this is derivative of the first. And here you need to be careful, because your brain wants to like do calculus on the r squared, but r is a constant for this problem. X is the variable. We are differentiating with respect to x. So you have to say, okay, if I'm taking the derivative, this is just negative 2x. The derivative of the first times the second plus the first times the derivative of the second, which is just 1. Cool? Yep. And then this pi over 3 is out at everything. All right, so let's just double check that. The first, the second, the first. Yep. Okay, so now, I think now I might factor Ethan because there's an x plus r here, right?
X plus r, x minus r.
Mm-hmm. So this is, but you don't have to. I mean, anything you do would work here. But this is r minus x, r plus x. And so I'm factoring so I can make a sign chart. So what do I get? If I factor out this x plus r, I'm left with negative 2x plus r minus x, otherwise known as r minus 3x, basically, right? R minus 3x. And now I'll maybe just pull out one, if I'm being really fancy now, maybe I'll pull out a negative 3. So what I get is, if I pull out a negative 3, negative pi x plus r times, since I pulled out a negative 3, it would be x minus r over 3. Okay. This is the best, I think, way to write the derivative, because it's just a quadratic. And what do I have to say about this quadratic? Well, it has 2 roots, one at negative r and one at r over 3. And the leading coefficient is negative, so it's negative, positive, negative. Now, of course, it makes no sense for r to be negative, but it's still helpful to put it on your sign chart anyway, because it helps you make the correct sign chart. And so what was the overall goal for this problem? To figure out when the volume is maximum, and where do we have a relative maximum? At r over 3. So my conclusion is, as the derivative of v changes sign from positive to negative, v has a relative max at x equals r over 3. So the takeaway from this entire problem is that it was a little bit weird to call this variable x, because it has we don't really usually think of x as something like important. X is just like the distance below the center of the sphere to the center of the base of the cone. But algebraically, that turned out to be the best variable. Well, anyway, what I've now learned about that x is when it's 1/3 of the radius, that's when I get the biggest cone. Cool? All right, now just to finish off the problem, you have to do a little bit of math. if I know that x is r over 3, then that means that this guy right here is like root r squared minus r over 3 squared. So that's like 1 minus a ninth is 8/9. So that's 8/9 r squared, the square root of that. And so you could just leave it like that or whatever. I guess it's like 2 root 2 over 3 r. So the answer to the problem is that the height of the cone should be 4/3 the radius of the sphere, and the radius of the cone should be 2 root 2 over 3 times the radius of the sphere. And then to put it all together, you just find the volume. What's the volume? It's 1/3 pi. The radius squared, it just becomes 8/9 r squared times the height, which is 4/3 r. And so my overall volume is 32 pi r cubed over 81. All right, classic calculus problem. Find the largest cone that can fit in a sphere, find the biggest sphere that can fit in a cone, find the biggest cone cylinder that can fit in a cone. All of these are like kind of all in the same sort of family of problems that you need calculus to solve. All right, how are we feeling? Good. Let's learn a new thing that's not really a new thing. So, one of the things that first inspired us to, our head's like right in that, whatever. One of the things that first inspired us to, I'll just wing this, study differentiation was position, velocity, and acceleration problems.
Are we doing the other one?
No. But what we're going to, now that we have found, now that we're really good at taking second derivatives, we can begin to analyze like these motion problems. You almost don't even need to write, you could write this down, or you could just pay really careful attention. It's really up to you. Because everything I'm going to say is sort of common sense, but there are some like kind of tricks. And then we'll do a problem together. So, all right. So, what we have, what I want to discuss is motion in one direction. So this is the simplest kind of motion in which we have a number line, and there's a 0 point on this number line, and we have positive values and negative values. And we have an object, and that object is moving back and forth along that number line. Okay, so at any given time, the object is somewhere maybe on the positive side or somewhere on the negative side or 0, right? Okay. And usually we let the little, the letter S refer to the position of the object at time t. Okay. Well, what is the derivative of the position with respect to time? What would we call that? Velocity. By definition, the velocity is just the derivative of position. And so, great. All right, what does it mean if my velocity is positive in the context of this motion in one direction? No, careful. If my velocity is positive at a given moment, yes, Ethan?
You go right.
Yeah, if my velocity is positive, it means the rate of change of my position is positive. So my change in position is positive. In other words, at that moment, my position is increasing. It's helpful even to say the word like position number, because since we're only moving in one direction, I'm capturing my position with a single number. If my position number is negative, it means I'm somewhere on the left. If my position number is positive, it means I'm somewhere on the right. If the derivative of position is positive, then it means that my position number is changing positively. In other words, moving to the right. Are we good? Okay. What does it mean if my velocity is negative? It means that my position is decreasing. That's another way of putting it. And if my position number is decreasing, it means I'm moving to the left. Cool? Okay. So this means moving right. This means moving left. Good. All right. What if my position is positive and my velocity is positive? Can someone say in words like what's going on? Eric, what's going on if S is positive and V is positive?
You're on the right side of 0 and then you're moving right.
Exactly. You're on the right. In other words, you're in positive territory and you're moving right. Okay. What if your position is negative and your velocity is positive? Yeah.
You're on the left and you're moving right.
Yeah, it means you're on the left and you are moving right. Okay, and then like the others are just like more of the same, right? Okay. So all right, question that requires a little bit of thought. When are we moving towards the origin?
When your position and velocity are different.
When your position and velocity are different. Does everyone see that? I'm moving towards the origin when I'm either on the right moving left or on the left moving right. So either when my position is positive and my velocity is negative, or my position is negative and my velocity is positive. Cool, cool? Okay. What is the second derivative of position with respect to time?
Acceleration.
Yeah, this is just by definition then, the derivative of velocity, and this we call acceleration. All right, now we have to be really careful because acceleration is like a word that normal people use in normal English, including you guys, but it is also a very technical term that we're now defining precisely. And since a derivative can sometimes be positive and sometimes be negative, an acceleration can be positive or negative. But it doesn't always mean maybe what you think it means. For example, well, first of all, off the top of your head, what do you think it means if the acceleration is positive? Oh yeah, that's actually true. You guys are giving me the correct answer. But just like in normal words, what do you think it means if the acceleration is positive? Speeding up. What does it mean if the acceleration is negative? Slowing down. Okay, it turns out that's not true. It's more complicated than that because the signs don't work out the way you think. So we can tell a couple of stories. So here's one story. Imagine that I am going 5 meters per second, and then a couple seconds later I'm going like 8 meters per second, and then a couple seconds later I'm going like, I don't know, 12 meters per second or something like that. What is the sign of my velocity? Velocity is positive. What is the sign of my acceleration?
Positive.
Also positive because my velocity is increasing. And what would we say is happening here? We are speeding up. Speeding up is good because since speed is always positive, speeding up is unambiguous. Everyone knows what speeding up means. Alright, what if I'm going 15 meters per second, and then I'm going like 10 meters per second, and then I'm going like 9 meters per second or something like that? What can I say about my velocity now? My velocity is positive. What's my acceleration? Negative. And you guys are all like, duh, of course, because my velocity is decreasing. Alright, so this, and how would I describe this in normal, unambiguous human language? Slowing down. Good. Alright, am I like in framing stuff all this time? Yeah. Okay. What if, now here's where it gets weird, you have to be careful. What if I'm going, and now I'm going to draw my arrows going the other way. What if I'm going negative 10 meters per second, and then I'm going negative 20 meters per second, and then I'm going negative 25 meters per second? What is my velocity throughout this interval? Negative, because of course velocity is negative. Also moving left. But what's happening with my acceleration?
Negative.
My acceleration is negative. Good, because velocity is a number, and that number is going down. But going down in the sense of becoming less, more negative, right? But it's definitely decreasing velocity. Cool? Alright, so acceleration is negative. Yet, what is happening here? We are speeding up. Good. Okay, whereas a different story, what if I'm going negative 20 meters per second, and then I kind of chill to be only doing negative 12 meters per second, and then negative 4 meters per second. What is my velocity? Negative. What is my acceleration? Positive, in the sense that my velocity number is increasing. But increasing means becoming less negative. What's happening in normal terms?
Slowing down.
We are slowing down. All right. So so you can't. The sign of the acceleration doesn't tell you whether you're speeding up or slowing down in isolation. It needs to be compared with the sign of the velocity as well. Is everyone seeing this? Can someone summarize? When am I speeding up in general? Gabe?
When the signs of the velocity and acceleration are the same.
Yes. I'm speeding up when my velocity is positive and increasing. Or when my velocity is negative and decreasing, as in becoming less negative. Okay, some people get this immediately and some people have some struggle with it a little bit. When am I slowing down? When my velocity is positive and decreasing, or negative and increasing, because that means becoming less negative. Robert?
Is this story told in respect to the arrow?
Good. What? Yes. The story was told verbally as I was talking, so yes.
No, like from what, like do you read the story left to right, or like do you follow the arrow?
Follow the arrow.
I don't understand that question.
Follow the
Good.
arrow.
Follow the arrows.
Follow the arrow.
Good. Everyone take a gigantic packet, and we have 7 minutes. Just enough time to do, I guess, one problem is all we're going to do. This is a combination of, back before they changed the calendar, this was the Wallops packet. But now we don't get to this point anymore before Wallops. And Wallops was kind of early. Oh yeah, and then change that to like 18. So what we have are some curve sketching problems. You now know how to do everything in this packet, but I'm not assigning all of it all at once. And there's a bunch of optimization problems. But I would like you to turn to page 8. Page 8. Which is number 9. And everyone do this problem right now. Go. What? You need to stay awake in class. Good, do the problem.
Let me watch versus like oh boy.
What's that?
But like variables get reduced. And it might be
And what kind of information do we need to like do this problem? Like just in general, kind of. Like I need the, derivatives wouldn't hurt, he says. I need the velocity and I also need the acceleration, right?
Yeah.
And I need to compare them. So it might be a good idea to do kind of what we were doing with the curve sketching. Take the derivative, get the velocity, make a sign chart for velocity, take the derivative again, get the acceleration, make a sign chart for acceleration, and write them directly underneath each other so you can compare.
Wait, can you repeat that?
Yes, take both derivatives, factor them, and just like we did with curve sketching, make like a number lines right next to each other.
plug it in.
You can't be able to.
Wait, which one are we talking? I need a point. Wait, okay, so. Oh, yeah, you're right. How'd you get 15? Just get 15. It's just 15.
Yeah, just 15.
Thank you, I understand that.
It's okay, I related that.
Yeah, so personally, I just take the derivative. Like the first thing I do is just take, that's kind of what I left space for on the top. Just take the derivative, factor it, take the derivative again, factor that too, and make sign charts, labeled sign charts, for the velocity and acceleration right on top of each other so that you can compare them. Is that what you guys got for the acceleration and position? Or, sorry, velocity and acceleration? Okay, cool. Alright, so can we just kind of like do this whole thing real fast before the bell rings? What is the position of the particle at time 5?
15.
Yeah, you just plug in 5 and you get 58? I'll take your word for that. Is it 58 or 48? 15?
15.
Alright, good. What is the average velocity of the particle from t equals 0 to t equals 5? That is not a calculus question, right? Average velocity on the interval 0, 5 is just the change in position over the change in time. So it's s of 5 minus s of 0 over 5 minus 0. So it's 15 minus negative 5 over 5. So it's like 4, right? No, it's, yeah, 4. That's what average velocity means. Average velocity just means change in position over change in time. All right, what's the instantaneous velocity of the particle when t equals 4? It's basically just asking for v of 4. What is v of 4? 9 meters per second. Okay, when does the particle change direction? At 1 and 3, right? If the velocity is positive, we're moving right. Then at t equals 1, we change to be moving left. Then at t equals 3, we change to be moving right again. Cool? Okay. So at t equals 1 and t equals 3. When is the particle moving left? On the interval 1, 3. When is the particle moving right? Negative infinity to 1 and 3 to infinity. Okay, and now the only...
So you say 0 this time is never negative.
Time can be negative. Good. For example, before you were born, Pujing, I had a lot of great times.
Sure.
All right. When is the particle speeding up? This is the only interesting problem on this page.
1 to 2, you 2 to infinity. 2 to infinity.
No, Tarun missed the point of our whole conversation over there. When are we speeding up? Yeah. No.
No, it's 1.
1 to 2 and 3.
No, wait, hold on. This is the only hard question on this page. Bell's about to ring. When are we speeding up?
1 to 2.
When my velocity is positive